Hello and welcome. I'm Mohammad Afzal Shadab, and today I'm going to talk about the first project highlights. And in this project, we used second and fourth order central differencing to solve heat equation. And for that, we have also used iterative solver, namely Jacobi and Gauss-Seidel. And let me walk you through what I did. So I'll start with the programming language for this project. And my research was in Python. So if I knew C++ earlier, I would have been in a good shape while learning Python. However, I was a different person coming from Python to learning C++. So as everyone does, I first started to learn C++ in videos, but the video was a little long. So I'd like to acknowledge Shreyas and Allison for their help with learning C++. And I know Fortran, but I had never worked in C++. So that was something new which I learned. So let me start with the main driver routine of my project. And it looks a bit weird, but I'll walk you through each and every section, and I'll try to make it a little less boring. So in my driver routine, first I included the libraries. Some of them were inbuilt libraries. Some of them I made some function files and I'm calling them as header. And after I included all the libraries, I ran the main function. And the first thing I did was importing the GRVY timer. As you can see here, the parser, which is a GRVY input timer class. And then I parsed the input file using GRVY. So input file input file.dat was being parsed, and then I started parsing the variables like mesh dimension. I'll talk about input file later, but there's some more main driver code, and you can see some more variables being parsed. And after I'm done parsing, the next thing was defensive checks. For example, if the dimension is not 1 or 2, we have to throw an error. Or if order was not 2 or 4, we still have to throw error. And invalid cells, or if your minimum x is greater than maximum x, it has to throw error. So these sort of defensive checks to be sure whether we are working in the right direction. The next is checking the output mode. If it is 0, it is a silent mode. If it is 1, then it is a debug mode. We are debugging and we want to see each and every metrics, and it is printed in MATLAB supporting form. So you can just copy paste it in MATLAB and you can see whether your solver is working or not. Next is dynamic memory allocation. And this is where I struggled the most because I was not known to this concept of pointers. So Shreyas and Allison helped me learn it. So thank you to them. And after I dynamically allocate the arrays, I assemble the matrices, A matrix, which is the left-hand side matrix, and Q matrix, which is the right-hand side matrix. And I also assemble the exact value, and exact value comes from MASA library. And that is method of manufactured solution. And then I solve AT equals Q, where A is that squared matrix, Q is a vector, one-dimensional vector, depending on what size we have, whether it's 1D or 2D. And this uses either Gauss-Seidel or Jacobi method to solve the heat equation. Next is the verification mode check. If verification mode is on, then we'll get our output as a verification mode being on and the L2 norm of the error between the computed value of temperature and the exact value of temperature coming from MASA library. And if we are in debug mode, then we do the printing part, which I discussed a few seconds ago. And yeah, and finally, we write the output to a file, and we can change the name of the file in our input file. And finally, we deallocate the memory like good programmers. We don't want the memory to stay stored. So we finally remove everything. Okay, so this was my main driver routine. It is not a monolithic code. It is very modular. And these are function files which you might find in my GitHub repo. Next is the input file. Input file has two sections. One is the mesh and other is the solver. And these are dimension, the x minimum, x maximum, and the grid number. If it is two-dimensional, it's 100 by 100. If it is one-dimensional, it's just 100. Solver, what sort of finite differencing I'm using, second order or fourth order central difference, which iteration method, whether it's Jacobi or Gauss-Seidel, if I'm using verification mode or not, and output mode, the coefficient of thermal conductivity, watt per meter Kelvin is the unit, and the epsilon or the tolerance for Gauss-Seidel or Jacobi solver. And we also put a cap on the number of iterations in these iterative solvers up to 250,000. And finally, the name of the output file. We can change any of them, and that will correspondingly affect our simulation. Now coming to our favorite order of convergence study. So on the left, you have one-dimensional results. On the right, you have two-dimensional results. And as you can see, the second order is perfectly, it is close to second order, because this is a fit from a Python function, and this is fourth order. And so you can see that the error reduces very rapidly, even for same number of n. And if you go to the right-hand side, you'll find that we still achieve the same order of accuracy. So second order gives around second order accuracy. Fourth order gives fourth order, close to fourth order accuracy. And if we do the same drill for Jacobi, we cannot do fourth order with Jacobi because that doesn't converge. So we are just sticking to second order Jacobi. And we find that we are getting the expected order of convergence, 2 in both the cases, for 1D and for 2D. Next is the time. For 100 by 100 mesh, fourth order Gauss-Seidel for one Skylake node and 48 cores, the wall clock time was around 3,000 seconds. And here's the GRVY timer output, where Gauss-Seidel is taking the maximum around 97.7% of time. And then the printing of these matrices. And finally, we have all the other small subroutines in our main driver file. You can also see that L2 norm is being called by about 45,000 times. So that's quite interesting, because we use that for our convergence calculation inside the Gauss-Seidel loop. Next is the 2D solution. So we used boundary conditions from MASA library, depending on whether it was 1D or 2D, and it was second or fourth order. And as you can see, that this is the solution, which has sort of a sinusoid if you go from one point to the other point, and on at y equals 0.5 and at x equals 0.5, you will get a full sinusoid. And next is the Vel Grind Summary. And Vel Grind is for memory error detection. And we have used it for n equals 25 by 25, fourth order Gauss-Seidel, one Skylake node, 48 cores. And this was our heap summary, and this is leak summary. We are definitely leaking a little bit, and we are, but the good part is we are not having any errors. So we don't have zero. We do not have any errors. So that's a good thing. And lastly, some lessons learned. One thing I realized that modular coding is more interesting than big monolithic code, as Dr. Carl Schulz suggested. And I was not used to using GitHub back in the day. I used to use it just for sharing my code, but now I'm using GitHub way more than I used to. So that is, I think, one of the important takeaway from this class. Next is I wanted to learn C++. I knew Fortran and C. C was the first language I learned around 8 years ago, and I never used it after that class. But I used to use Fortran, but I think C++ is a great language, and I definitely learned a part of it while working on this code. I started with metrics assembly and then solvers, because I wanted to compare my my results with the MATLAB results. So that was my starting point. And I started with basic functions, which were easily comprehensible, but I got stuck with pointers. So there, Allison and Shreyas helped me. And if given a chance, I would do the same thing again. So I'm really happy the approach I took and the guidance I got from my friends and Dr. Carl Schultz. Finally, the wisdom I'd like to share is high order methods are the future, or maybe they're being used popularly even now. In academia for sure, but in industry, they are fixed to second or maximum third order. But it's mainly second order muscle monotone upwind scheme for conservation laws. That is pretty famous. But one thing we realized with this project is high order methods are not as expensive as people might think compared to low order methods. I know they are less robust because they might break down if there is a shock wave very easily, although this was an elliptical problem, so we didn't come across that, but these are definitely less robust. But there are promising developments being made in this field, like uh, DG plus Vino, or this high order shock capturing scheme. We have so there is a significant advancement, and let's hope NSYS and COMSOL integrate these in future. We get high resolution on same mesh. So what we generally do is we refine the mesh to get to the same order, or say to get to see good results. But the problem is sometimes we actually lose the scale where that governing equation is defined. So if you are working with Navier-Stokes, and if you reduce your mesh size to say 10 to the power minus 6 meter, you are not in a continuum regime. You are in a near continuum or maybe non-continuum regime, where there is no fluid particle inside your control volume. So grid convergence is not the most nicest way uh, to get good results, because sometimes we lose physics behind. So there are cases where high resolution is needed even for bigger mesh size. And lastly, if we have some convergence based simulation running, we get to very high convergence with these high order methods. So that is the only wisdom I'd like to give, because I have little experience with it. Other than that, I think I learned a lot in this code. I feel that I have never really worked with any of what I learned in this course. So that is probably my takeaway, and I'll keep on doing it. Thank you very much. And if you have any questions, please feel free to let me know, and either email me or email me. That's probably the best. Thank you very much, and hope you have a great day. Thank you.